is so excited day for all of you, I know. Today is the second day of the session on self-driving car. Before we start the session, I would like to introduce our resource person. He's Pramudita Aravinda. He's graduated from University of Mortua in computer science and engineering. He's a seasoned software engineer with 20 years industry experience. And currently he's working as a senior tech lead at Zone 24/7. And also he's a world finalist in Emerging Cup 2009 under robotic and algorithms. Currently leading a Sri Lankan and American collaborative team for the final round of Space Robotic Challenge Phase 2 conducted by NASA. We wish you all the best to win the competition and to make Mother Sri Lanka proud. Over to you, Prabhudita.
So, to recap what we discussed on last week, Nadi, can you remember what we learned in last week?
Yes, Pramadita, it was so interesting actually. We learned about the current status of self-driving vehicle project initiated by different level of companies. And also we got an idea about level of different systems. And we learn about high-level software architecture that make up self-driving car. And we also had small coding demonstration how to simulate a prototype.
Yes, you are correct, Nadi. So, let me quickly go through to an announcement. So I have uploaded all the material from last week session into this GitHub repository. You can note down that and take a pull from this repo to access what we discussed on last week. I will give you a couple of minutes to take note. I will also take a copy of this to and drop a message to WhatsApp groups as well. So let's discuss what we are going to discuss today. So remember, last time we do a steering control demonstration using computer vision. So in that, we have explicitly programmed how to identify lane lines and control our steering accordingly. Today, I will start with a small coding demo that will allow us to teach a computer to handle steering by observing someone else doing that. So, in the last week, what we did was the traditional programming. So what we did there was that we explicitly give the instructions how to identify lane lines and how to act upon that information. So we explicitly tell that, okay, this color is lane lines, this color is not a lane, and so on. So in that case, if we tell that a certain color range is a lane line, the computer is going to omit all the other colors, even if the lane line was, say, discolored due to the rain damage or the sun has worn out the colors. So in that case, it won't work. The other thing is we show and let the computer observe our actions, how to do something. This is basically from the realm of machine learning. So here what we do is we gather a lot of data regarding what the computer will see and the appropriate action at each time. So without further ado, let me pull up my development environment and show you what I am meaning. Let me increase the code size. So here, first what we do is, let's do a little bit of cheating and use inherent information from the simulation system and use a PID controller to control a vehicle appropriate. At the same time, we will capture the information, mainly the main camera image, and also we will gather steering values. Let me run this demo. My apologies, I think there was another instance running. I think it's no problem. So here what we do is take an experienced example driver controlling a vehicle and gather data while it's happening. Okay, so it have gathered a lot of data here. Corresponding images. And it also captured against each image what was the applied steering angle at each point. So then what we do is train a deep learning model based on a given framework, basically Keras or TensorFlow. So I think you are familiar with these technologies from the machine learning session we had in the beginning of this series. If you haven't attended that series, I suggest that you go and review the recorded session. I wouldn't be able to do live machine learning training right now and do a replay. So instead of that, I will show you a previous session, time I have done this and taken a video. So I think while we are waiting for the video to load, we can open up for any questions the audience already have, or we can also have a Q&A session at the end of the session as well.
If you have any question, you can raise them to our chat box. Pramodita, we have one question. Pramodita? Pramodita, can you hear me?
Yeah, we can answer that.
Yeah, we're having one question from the audience. So when we use in machine learning to implicitly learning the driving, does a human first drive the car? He's asking then implicitly learning the driving.
So there are two approaches. Yeah, so there's two approaches. The way I right now demonstrated is actually it's supposed to be a human to drive and the computer to learn from that. So this is behavior cloning. So actually you are cloning a behavior of someone else. So if you train a deep learning model this way, it will be as good as the original human drive. So basically, like if you train the model using maybe a typical Sri Lankan three-wheel driver, obviously it will take a lot of U-turns in the middle of the road, taking left turns while the signal light is indicating right-handed. You know what I mean, right? So
Yeah.
if you train using a driver, the model will exactly imitate or closely imitate the original human driver's behavior. But there is another mechanism that I will explain a short while in this demonstration. Actually, I wouldn't be doing a live demo, but I will discuss about the approach, which is called reinforcement learning. So in that, we let the computer to play in a simulated world and learn from mistake. We let it to do mistakes and then learn from that experience. So in that case, there is no need of gathering data from a human driver. So that's called reinforcement learning. Sometimes you build deep learning models from both ways sometimes. I mean, you first maybe build a rough or basic deep learning model from deep learning or like behavior cloning, I mean, then fine tune that model using reinforcement learning. So that kind of things can be done, but you need to understand what's the difference between these two models. So
yeah, we got an idea about it. Another question, Prabhadita, I have another question. If the system depends on the training data set, right? Is it depend on the weight of the data set?
can you please come again?
It's like that. If it's gathering all the information, it's been all the data while we are driving or while we are traveling somewhere. So if it's depend on the data, it's depend on the weight of the. Commonly how many data we can measure the data. So weight of the data, is it depend on the weight of the data?
Yeah, I mean, it's like this. I believe what you are referring to is that, let's say it has lot of highway driving data, but very limit of rural road driving examples. So in that case, the model will tend to work better on highway driving, but not on rural driving. If your system is actually supposed to work well on both cases, you have to supply it with the model training with approximately equal amount of rural road driving as well as the highway driving, and also has to have roughly equal amount of different weather conditions. So if your model training data had little amount of rainy road driving, so it will not work properly on such situations. So it has to be balanced.
Okay. Thank you, Brahmaditya. We are having another question. Can we do behavior cloning in the provider simulation environmental alone without any real-world human driving input?
The thing is, if you do training using behavior cloning in a simulation environment, if the simulation environment is not exactly realistic, so the simulator I am using right now, as well as the simulation I am showing in this example, I believe that you can see the video playing now.
Yeah.
In that case, it is not exactly realistic. I mean, it's like those Windows 95 era video games. So in that case, a model trained using such an input will not work properly on a real environment. But there are some advanced simulators that actually needs a lot of computing power. That's basically the main reason I'm not using that for these demonstrations. That give you even lens flare. You know that when a camera points towards a little bit towards the sun or very bright light, it gets that color artifacts, that the rays and so on. So there are simulators that actually allows you to get such realistic information. So if you trained using such a simulator, then it will somewhat work on a real world vehicle. But usually what you do is first take a basic level model using simulator training, then fine tune it using actual human driver and actual data. So that's the way usually the actual corporates like Tesla and Waymo doing this model training. They first take a basic model using a simulator, then fine tune that model using input from real world driving.
Thank you, Brahman.
Yes,
yes, it was clear to us. We have another question. How can we use semantic segmentation instead of behavior cloning deep learning model?
Yes. You can still hear me properly, right? I mean,
yes,
there's
no interruption.
A bit of noise because it suddenly started to rain a bit here. I believe my voice is higher than the sound of the rain.
No, your voice is so clear.
Yeah. Okay. So basically, the way you use this semantic segmentation is similar to how you use with computer vision to take the lane markings. So the advantage of using semantic segmentation instead of computer vision based approach is the semantic segmentation tend to handle a little bit better than traditional computer vision with new unknown data. I mean, let's say you had white color lane markings in the previously, and suddenly the government decided to mark all the lane markings in yellow color. So if you had a computer vision model, depending on how much additional margin you have left in the color range, it will not detect new colors. But the semantic segmentation models might pick up new situation little bit better than traditional computer vision models. That depend on how whether if you had overfitting of your model to exact white color, then it will not properly work. But if you had trained it properly, the semantic segmentation will work. But what you usually do is you take semantic segmentation, and from that you get the lane curvature and lane offset of the vehicle. Then use traditional calculation model of computer, I mean the vehicle control and make a control. So in that case, that's a little bit of half of deep learning, half of traditional computer programming. I believe that you got the idea.
Yes, Pramodita, thank you so much.
Okay, I think that's it. I think
you can continue the session. Questions are over.
So let's move into the next one. I think my browser got a little bit unresponsive. Sorry about the small technical difficulties. So to elaborate on how actually the system works with this end-to-end driving or behavior cloning models, we let a human driver to drive the vehicle, take the training data and make a supervised learning model. So the model input will be camera image, and we process it through a deep learning model, and its output will be steering angle, whether it's to be turned to left or turned to right, or how much. So that's the basic idea of this behavioral cloning. So that's two approaches that we can use for steering control. Now let me briefly explain you how we can control the speed and braking. So basically we speed and brake with response to vehicles moving in front or moving in the back. So for that,
Mudita, sorry for
yes,
interruption. It's better to change the mode into presentation.
sorry about that. Thanks for reminding me. Okay. So basically we control the vehicle's speed and braking in response to vehicles moving in front or in back. Basically, mostly of the time, the vehicles moving in front. For that, we will need a sensor that can capture the distance to vehicles, the other vehicles and obstacles. So can you remember from couple of sensors we discussed in last session that would be good in such a situation? Yes, LiDAR or radar. So in current implementations of vehicles, they usually use radar because that's better in terms of both cost wise as well as accuracy. In this simulator, we will have, however, only have a LiDAR sensor that will give us a set of points to obstacles in the environment. Let me launch the simulator and show you how that works and give you the measurements. So this is our simulator. And so I'm not exactly sure whether you can see that there is a lot of red lines emitting out from the vehicle right now. So that's the simulator is showing how the LiDAR points going out in the environment and incident in the environment. And at the same time, it will give us a set of values. Let me print a couple of measurements from there. this LiDAR object will have a set of measurements in an array. Let me print the first value and last value. So as you can see, each measurement will have 3 values. One is the distance to the obstacle, and the horizontal angle and vertical angle. So horizontal angles will be from 0 to 360, actually 359, because 360 will again become 0. Horizontal 0 will be directly forward, and turning clockwise when you see from above of the vehicle. Y angle will be from bottom to up. Up is forward, I mean positive. I have used a LiDAR with only single plane. Here in this advanced way of using this simulator, we have to give configurations of each sensor that we like to use. I will also upload this file also to the GitHub repository, so you can read through the code documentation in your free time. So then what we have to do is take from these LiDAR measurements the distance to the vehicle in front, according to the distance to that vehicle, we can control the speed of the vehicle so that the two vehicles stay in roughly same distance. Let's say if it is the distance is getting lower, we can reduce the speed. If the distance is getting larger, we can increase the speed. Likewise, so basically you can use a PID controller there as well. So I'm not going to do the coding right now, but the code will contain the to-do points to point out how to do the coding, and you can try it out in your own free time. So let me go to the advanced topics that we can use in the programming self-driving vehicles. So as we already briefly touched upon, one such approach is reinforcement learning. So here what happens is we need to define a reward function. So that should capture how safe is the vehicle right now, how efficiently it is driving, and how comfortable. So basically, the safety is that it's not violating any traffic rules. So if it is violating traffic rules, the reward function would be less. I mean, if it is violating traffic rules, or if it is crashing into other vehicles, etc., that would add a minus value to reward function output. If it is driving efficiently, one efficiency is whether it is driving as fast as possible. So if it is speed is higher, the reward will be higher. But at the same time, if it is exceeding the legal speed limit, that will add a negative value because of unsafety. The other thing is whether it is comfortable. Comfortable means whether it is driving in a erratic, or I mean in a jumpy way. If it is flooring in 1 second the accelerator and then applying high level of brake force in the next moment, that becomes a uncomfortable drive. So if that's happening, that reward function also gets a negative value. So the art of the reinforcement learning lies on crafting out this reward function. If you created the reward function that doesn't capture all the information properly, or if you are biasing one aspect more than other, then your reinforcement learning model going to work inefficiently or not properly. The other thing is this only can be done safely on a simulation environment, because in real world you don't want a vehicle or a driver actually doing mistakes on a public road. Even if it is unsafe, and even if it is in a safer environment, I mean a private environment, still if it is going to crash, it's going to destroy your vehicle. So what you do is you run this on a simulation environment, and once the model is working properly, you still try out it in a simulation environment, and if you are satisfied with the results, you take the trained model into an actual environment. So that basically captures out the basic topics I would like to discuss today. Nadi, if there is any more questions, we can go to answer.
If you have any question, you can raise it to chat box. There's no any questions yet.
Okay.
We can go ahead, Pramudita.
Yeah. So I think we can
There is another
the
question.
chat. Yeah. Okay.
What are other open source simulation environments?
Okay. There's one simulation environment called Carla, CARLA. That's somewhat good. There's also a Microsoft simulator called, I think, ARSim. Those are the two mainly open source, and I think, yeah, they are asking for open source. Open source simulators. Color simulator is open source. I'm not exactly sure about the Microsoft AirSim, whether the simulator itself is open, but I think you can write down any plugins, etc. if you wanted to. There's industry level state of the art simulators as well, which are not actually open source, but on industry level from NVIDIA, and obviously the big companies using their own internal simulators as well, which are actually almost true to the real world environment, but at the same time you need to have a quite good computing power to run them as well. So I suggest, if you are doing any serious work, to check out Kala simulation environment in your free time.
Thank you, Brahmadev. We can go ahead.
Introduce them the challenge as well. Shall I introduce what they are supposed to?
Yes, Brahmadita.
So to measure the how much learned the attendees on this challenge, on this session, we will give them a small coding challenge that they can attempt to win fabulous prizes, like in other sessions we did. So we will upload the challenge instructions and starter code that they can start and working on, and open the challenge on I'm thinking of like tomorrow 6 p.m. and my suggestion is to run this challenge for, say, 14 days. That would be good, right?
Yes, it's great.
Yeah. So you have to, you need to mark your calendars that the challenge will open tomorrow, that is 6 p.m. and your solutions need to be submitted on or before 20th 6 p.m. So basically challenge would be like this. It would be on this same track, same environment. Your challenge will, your code will need to handle both steering control as well as drive safely on right hand. Let's for the simplicity, we will follow the US traffic rules. And your vehicle needs to stay on right hand lane. It cannot move into left hand lane. We will start the simulator with the AI controlled or computer predefined model control vehicle moving in front of your vehicle. So there will be a vehicle moving in front of your vehicle. So your vehicle has to follow that, should not crash into it. And for simplicity, we are not considering about things like advanced movements like overtaking, etc. So that will be the basic challenge rules. There will be a instruction document containing in the same GitHub repo. We have this all demonstration code contained. Basically, you can combine the three demonstration code I have to build this solution. But you have to do some trial and error and kind of fine tuning to get correct colors of the road and PID tuning, etc. For steering control, you can either use computer vision based demonstration code or deep learning model. There's no problem. The scoring will be how long your model or system will capable of running before either crashing into a barrier or to the vehicle moving in front, or before crossing the middle road lane. If there is a tie, that means if your vehicle capable of driving an entire circle in this track, we will have a leading vehicle speed increase to the maximum and see who can survive with highest speed. That will be the tie breaking criteria. So stay tuned. These instructions will be contained in the challenge package that will be open tomorrow 6 p.m. So that's it. Let's see your code on the track. I think
yes. Okay, Pramudita. Now we know about the challenges. I know you waited until this moment to know about the challenges. This is so impressive. There are a lot of gifts for you. You can win them. This is a golden opportunity for you. Don't miss this chance. Try to do this and win it. If you need to view our previous session, what you have to do is you have to go to our YouTube channel and subscribe it. You can preview this on YouTube. So if you want to get updates from FB, what you have to do is you can view our FB fan page. So thank you very much, Pramudita. Today is very impressive day. Actually, I got so many things, new things to my mind today. Thank you so much. This is a really good opportunity for you as well. And on behalf of all of you, thank you very much, Pramudita, giving us this chance. Thank you. Thank you for all of you.
Thank you, Nadi. And I would also like to make this opportunity to thank American Center for opening up this opportunity on behalf of everyone. And stay tuned for the challenge details, and have a nice day.